Doug Hubbard, again, needs no introduction to this group. He's a tremendous author, one of the first people that I found on my desperate search for risk information. In his third edition on how to measure anything, and the failure of risk management was another of his books. That was one of my favorites. And then Pulse is his third book. So I was realizing last night that SIRA has maybe an alternate acronym meaning, which is SIRA. So I'm really an author. Because we have so many writers that are speaking to us yesterday and today, of books and articles and everything. But back to Doug. He's with Hubbard Decision Research. He, too, is a creator of a methodology, applied information economics, which is applicable to industries as far-reaching as the Mongolian something or other, very, very, I don't even know, Doug will tell you, but entertainment, information security, he does work there, technology, cross industries applies his method. So he's going to talk to us this morning, and we're really lucky to have him, and I'm running out of voice. So everybody, let's give a warm welcome to Doug Hubbard. Thank you.
Thanks. Thanks. Great, I'm on? Good. So my challenge was, and I wasn't joking with Lisa when I said, yeah, here's my presentation. I finished it about 15 minutes ago. Only because I didn't want to be too redundant with Ali or the speakers panel yesterday, because Ali made some of the points that I'm making. And so I wanted to focus on different things. And then I realized I talked about some of this during the speakers panel too, so I want to talk about different stuff, and so I kind of rearranged a lot of slides. But let me start with a little bit of redundancy. So for some of you who sat with me at lunch and dinner, it might still be redundant. I didn't remove that stuff. You're going to have to sit through it twice. Let me ask you this. What's your single biggest risk? Anybody know? We talked about that one a little bit yesterday, right? What's your single biggest risk? I'll tell you at the end if you don't know. How about this? What's your most important decision? And what is your most important performance metric? Now, I asked this question of my pharma clients, medical device manufacturers, laboratory equipment manufacturers, mining and engineering clients, my economic intervention and agricultural intervention clients around the world, et cetera, environmental impact clients, government agencies, US and many others. I think you should give the same answers as all of them. So what answer would be the same answer for all those different industries and all those different problems? So this is familiar. I just want to tie it into part of the conversation from yesterday. This is a loss exceedance curve. So this is where Ali and I kind of converged, and we said, yes, that's the way to talk about it. That's the way to talk about a risk, okay? We're talking about a function relating the probability of some loss or greater over a range of losses. And it's mathematically unambiguous. Any actuary or statistician or econometrician or operations research guy will know what to do with this. We can add them up. We can do portfolios of these things, and the whole portfolio can have one of these curves, et cetera. So here's another thing you'd like to do in information security, though. You'd like to look at a bunch of risk or maybe a bunch of systems and look at particular mitigation opportunities and ask yourself, is this mitigation worth it or not? Now, there's some simplifying assumptions in these ROI calculations, but something like this would be useful. You want to know, do I get more bang for my buck here or there? So in effect, I have to monetize how much I shift that risk curve, right? This is ultimately what you want to do. So how do we do that? Because even though IT is only a minority of our work, and information security is only part of the IT work that we do, you actually share, this is something we've done a few times now. So how do we fill in the blanks? How do we get to the point where we're generating calculations, running simulations that actually generate those curves? Well, we know some things. We talked about the relative performance of different methods yesterday. In the power panel, I talked about it's never about whether or not to model something. It's about one model versus the other. If somebody's a skeptic of a model, great, but be a skeptic of the alternative model you're already using, which might be your expert intuition. That has a measured performance. Now, back starting in the 1950s, this guy named Paul Meehl, he started collecting a whole bunch of research, over 150 studies, actually closer to 200 by the time he died, comparing human experts in a variety of problem areas to simple statistical models. When he was at about 150, he could only find 6 where the human experts did just as well or slightly better than the simple statistical models. And these were things like predicting the failure rates of new businesses asking for loans, or the prognosis of liver disease, or the outcomes of sporting events, etc. So these are a lot of practical, real-world decisions that human experts often have to make. And simple models, and I mean linear models with 2 or 3 variables, were beating the humans in all these areas. Humans with 20, 30 years experience. They couldn't outperform the models. More recently, Philip Tetlock published his work a couple years ago. He tracked 284 political, economic, technology, military experts over a 20-year period, collecting just over 82,000 data points. Now, I've got a lot of big pharma clients, several big pharma clients, and they don't have phase 3 clinical trials as big as that in terms of data points. And he goes even further than Meehl. He says it's impossible to find any domain in which humans clearly outperformed crude extrapolation algorithms, less still sophisticated statistical ones. So it seems like it's done. What are we arguing about? We should be doing the math. We shouldn't be relying on that quite as much, on our own intuition, that is. So what do we do with this stuff? We should be populating simulations. We should be doing the math with this. We should be generating our risk curves, etc. So you all know what a Monte Carlo simulation is, right? I won't spend too much time on it. Well, you know, if you know anything about a Monte Carlo simulation, or if you don't, let me just give you the elevator pitch for it. This is the simplest explanation I've ever come up with. It's how you do the math when you don't have exact numbers. Now, there's a bunch of other ways to do some problems when you don't have exact numbers, and they have closed form solutions in some special cases, but in most even simple business cases or business decisions of some kind, you're dealing with operations where there actually isn't a closed form solution. There's no algebraically exact solution. You have to do sampling. So this is one way of doing sampling. This is one way of doing the math when you don't have exact numbers for anything. Now, I show a simple example here. Most of the models that we create will have 50 or 150 or more individual variables, and we're running simulations. The one you were talking about in Inner Mongolia was we're doing it's a United Nations project for computing the economic impact of a desert greening program in Inner Mongolia. It's called the Kabuchi Desert. They're replanting the whole thing. They're trying to figure out if it can be replicated in other parts of the world. So we're building this model, and we're about halfway through it. But we build similar models for other things. The one we just finished was the risk of that mine flooding in Canada that I mentioned, and some other cybersecurity examples right now. Also, the value of standards in the insurance industry. That's the other one we're on. So one of the reasons you do it is not just because it's the only way to do the math in most of the problems that we're going to deal with. People who build Monte Carlos are actually better at forecasting than people who don't. So there's 2 studies on this now. I won't go into great detail on them, but one in the oil industry and one from a bunch of NASA data. I wrote about them in the second book. So when we compare our models, one model being our human intuition, our human expertise, with, let's say, more quantitative models that humans still control, right? I'm not making a dichotomy here. It's not a false dichotomy here. It's really your unaided intuition versus aided intuition. Those are the alternatives I'm talking about here. But when we're looking at that, we have to consider several problems. We have to confront these. I mentioned this briefly yesterday, but there is a placebo effect in analysis. Just by going through something that seems structured and formal, you're going to feel better about your estimates. Some people use structured and formal as a benefit. They'll use it as a positive attribute of their methodology. Well, you know, maybe it's not scientific, but at least it's structured and formal. If that impresses you, use astrology. It's structured and formal, right? If that's enough, obviously it's not enough. We're also overconfident. I'll talk about that in a little bit. We're also highly inconsistent. I'll talk about a couple of different ways that we're inconsistent. And we have difficulty dealing with probabilities intuitively. That's where we need to do the math. So here's a few studies I mentioned about the placebo effect. So one was about horse handicapping. One was about giving more people more time and data about analyzing investment portfolios. And what you find out is if you give experts more data or allow them more time to analyze something, they start feeling better about their estimates, but they actually reach the point of diminishing returns very early in their process. And sometimes they'll just get more confident and their decisions can actually get worse. Now, algorithms, you spent some time talking about algorithms yesterday. Algorithms don't have that kind of limit. You can have lots of variables in algorithms. It never gets tired of how many variables are in it. Human beings can only synthesize so many data points, though. So, a little bit about overconfidence. Back in 1997, Gideon Gartner brought me in to train his analyst how to put probabilities on uncertain events. Everyone still use Gartner? Anybody using Gartner? Now, from what I understand, a few years ago, they quit putting probabilities on claims. Is that correct? You remember, does anybody remember when Gartner Group used to say, Microsoft will do such and such next year, 0.8p? You remember that? Some of you remember that? Okay. Well, when Gideon Gartner left Gartner Group in 96 or 95 or something, then his non-compete ran out and he started up Giga Information Group. So about the time he was starting up Giga Information Group, he actually brought me in to train his analyst how to do what they had always been doing at Gartner Group. He was suspicious that they were any good at it, just on anecdotal observations. There were it seemed like there were a lot of 0.9 probabilities they were getting wrong, in other words. So he asked me to train a group of his analysts, and we conducted a controlled experiment. We compared 16 of his trained analysts to 16 of their CIO-level clients. I asked them questions in January of 1997, things like, Steve Jobs will become president or CEO of Apple again by June of this year, 97 that was. Intel will release its 300 megahertz Pentium by June of this year. Okay, so we were asking these questions in January, and they'd answer each one true or false. These are true or false questions. And then they would state how confident they were in their answer. If you're 100% certain, you say you're 100% confident. If you had no idea, if it's a coin flip, you say 50-50. Otherwise, you say 70, 80, 90, something like that. So the first thing we did is we trained the 16 analysts, and then we made up these 20 IT industry-related questions and gave them to their untrained CIO-level clients, as well as the trained, calibrated 16 analysts. And then June comes along and we get the actual answers, and here's what we find out. Of all the times that the CIOs said that they were 90% confident, they were right a little less than 60% of the time. So the way you read this chart is this is their assessed chance of being correct, right? So they've got a bunch of responses in each of these bins. And then you look for each of those bins, what percentage did they actually get correct? Now, if you're perfectly calibrated over a large number of trials, you're right along this dashed line right here, this diagonal dashed line. That's perfect calibration. You're right 90% of the time when you say you're 90% confident. You're right 70% of the time when you say you're 70% confident. And the two lines to either side were the statistically allowable error given the number of responses in each of the bins. Okay? So 58 times they said they were 90% confident. They had a little less than 60% of them correct. 21 times they said they were 100% confident and got a third of them wrong. Now, if you have a 1 in 3 chance of being wrong when you say you're 100% confident, that's extremely overconfident. I mean, that's right up there with the overconfidence of physicians, which is the other most overconfident group I found. But CIOs were extremely overconfident. So how did the analysts do? Well, 45 times they said they were 80% confident, and they got 80% of them right. Most of the rest of their curve was within the statistically allowable error. The only exception is 17 times somebody said that they were 100% confident in some prediction, and one of them got one wrong. There's no statistically allowable error when you're 100% confident. You have to get them all right. Doesn't matter if you say you're 100% confident 500 times, you have to get 500 right. Okay? So there's no room for error in that one. The rest have some statistically allowable error. Now what's interesting is they were all trained, the analysts were trained using trivia questions. But we rated their performance based on their real world forecast they have to make in their jobs. So even though I was training them on trivia questions like, does a hockey puck fit in a golf hole, true or false, and I'd ask a large number of questions like that, they actually got better at assigning probabilities. Now, I was building on other research that did this, because research in this area has been happening since the 1970s. You can also apply calibration training to people's skill at putting ranges on things. So you can get a lot better at putting 90% confidence intervals on uncertain continuous quantities, like the impact of some breach. How long would an outage be? How much money do we lose per hour that we're out, et cetera? Those can all be ranges, right? You put those into a Monte Carlo simulation. But where do the ranges come from? Often they have to come from your expert intuition or the expert intuition of somebody else in the business, and they have to be trained, because without calibration training, people tend to be overconfident with ranges as well, which means their ranges are too narrow to realistically represent their uncertainty. So I mentioned that we have, as of now, we have a little over 1,000 data points. At this point, this slide I had 927 data points of people putting 90% confidence intervals on things. And when they take the first test, this is a 10-question test. Here's how the scores are distributed. Here's how you would expect them to be distributed if they were perfectly calibrated. You'd expect this kind of distribution. You'd expect about this many people to get 9 out of 10. This many people would get 10 out of 10. About this many would get 8 out of 10, et cetera, on the red line. But this is the actual distribution. So when you ask people for a 90% confidence interval, the actual distribution indicates that they respond as if you're asking them for a 50% confidence interval. That's actually more like what they do. But after training, you can see the distribution starts to match it a lot more closely. Okay? Now, it doesn't match it exactly, because I mentioned yesterday about 15% of people can't get calibrated. 85% are statistically indistinguishable from perfect calibration. 15% don't quite reach calibration. But 10% actually improve significantly, even though they didn't quite reach calibration, and 5% don't seem to improve at all. This is a 20-question test at the end, and this is a 10-question test at the beginning. The other way that we have to account for an error in human decision-making is we're highly inconsistent. And I briefly mentioned this yesterday, but we studied this on a few different clients in a few different situations. This is a client that was analyzing the probability of an R&D project going to the next stage of development or being released to the market. And we gave them a list of R&D project parameters, maybe a dozen parameters that you have to evaluate each R&D project by, and they would assess maybe 100 or 200 different projects. Now, buried in that list are some duplicate pairs. Number 11 is the same as number 98. And there's a few duplicate pairs, and I would ask a big group of people, maybe about this size, maybe the front part of this half of the room, and I would ask you over and over again, what are your responses to each of these? Well, they fill out a form. I don't ask them. They fill out a form. But you forget that some of the answers you just filled out are things that you've already filled out. And so you tend to put down different answers. So this chart shows their first answer compared to their second answer. The good news is that there's a correlation there. You know, they're not completely just putting down random numbers, but there's also a lot of inconsistency. So what if I could statistically smooth out your subjective judgments? What if I could just make you more consistent? And the way we do that is we build a regression model of the human judge. So when you think you don't have any data at all, but you've got experience, great, that's good enough. What I can do is I can build scenarios, simulated scenarios that you make judgments about, and I build a model that tries to predict your judgment. Now, what's interesting is if I build a model that tries to predict your judgment, the model of you outperforms you. Why would that be? Why does a model of us outperform us? I build a model that's supposed to represent your judgment, and then you compete in a side-by-side tournament in real-world estimates, and the model is outperforming us. Why does the model of us outperform us? It's consistent. If I want to make the model of us more realistic, I have to add a random number term. That makes it more realistic, because we just make up different stuff every day. Did I have my coffee yet? Did I sleep last night? Etc. All those things affect our judgment. So here's a number of studies about this. It's called the lens model. It was developed by a guy named Egon Brunswick back in the 1950s. And it's kind of obscure, but it's been applied in several areas. So there's real data about error reduction, cancer patient recovery time estimates, psychology course grades, mental illness prognosis, the chance of a business failure for small businesses applying for loans, et cetera. I've applied it to battlefield fuel forecast, also the entertainment industry, how much money new movies are going to make, and the a likelihood of success of agricultural intervention projects, et cetera. In each of these areas, you can find significant error reductions just by smoothing out the inconsistency of the human expert. Now, what I've done is I've built models in information security now based on a few parameters. So we would give someone a list of, let's say, systems, hypothetical systems that may not exist in your environment, but we've parameterized them. We've described them with a list of parameters. Maybe we say some things like this. You know, maybe there's some parameters having to do with one or more of these things, maybe several of these things. And we say, here's a system. Give me your probability that one or more events of a cost, a non-zero cost, or a cost exceeding $1,000 or $100,000 will occur in a one-year period. And they do this over and over again for several of the invented scenarios. And we build a model of your judgments. Now, this is without any historical data other than the historical data that's trapped in your head. So it's really an expert elicitation method. Now, we use this because of all the empirical data in other published, independent, peer-reviewed journals that show that lens models actually improve on human judgment. So I'm a sucker for empirical evidence. I'm going to use what works, okay? Now, what's interesting is if I build a model, this is actually one of the charts from Kaiser Permanente. So Richard Searson and I co-presented this among a bunch of other slides at RSA in 2012, I think it was. And this was one of the charts where we compared the model judgments to their the group average judgments. It turns out that the error between the model and the group average judgment was about as much as you could explain by their inconsistency. In other words, the only reason there's much disagreement between the model and the judges at all is because the judges are inconsistent. So the judges, in reality, have a pretty simple, implicit model they're going through. It's a simple linear model, a linear regression, because almost all of the variation of the model to the human experts is explained entirely by their inconsistency. So here's another way that we're inconsistent. You have to make choices about how risk averse you're going to be. But your risk aversion changes every day for reasons you're not even consciously aware of. You're more risk tolerant if you're around smiling faces. That's a reproducible experiment. You're more likely to be risk averse if I ask you to recall, if I took this half of the room and I said, write a little essay, one-page essay about some event in your life when you were really afraid. I take this half of the room and I say, write a little essay about some event in your life when you were really angry. So describe that. And then I give both sides of the room choices about bets they can make. Low risk, low return bets versus high risk, high return bets. Well, the group that just wrote the fear essay is more likely to choose the lower risk bet. The group that just wrote the anger essay is going to be more likely to choose the higher risk bet. That's called memory priming. So you ask people to recall an event and then you have them make choices, and it gives you a little bit of insight about how an emotional state affects choices. So these are things that actually change your mind. Sometimes you make the decision you make because you were more risk averse on Thursday morning than you were Tuesday afternoon, and that's it. Is that the reason we want to make our decisions the way we make them? Because I had my coffee yet? Or because you just won or lost an unrelated game of chance? Who gets involved in office polls? Anybody? Should whether or not you just won or lost an unrelated game of chance have any bearing on subsequent decisions that you make for your business? Well, we'd like to think that it doesn't, but it does. So here's some choices we can make. Which of those are preferable? If I imagine a bet with a series of outcomes. You can add some zeros to this if you like, if you want to think of it in terms of your business or something. But it's not clear that you should necessarily choose this one over that one. It's a function of your risk preference, right? How risk tolerant you are. So one has a higher mean return, but has a lower worst case than the other one. And so you can imagine comparing a series of distributions like that. And how do I figure out what my risk tolerance is? What's an unambiguous, mathematically unambiguous way to say I accept these curves and not those curves? Well, here's one way to do it. I was just telling Ali about this yesterday. He said you need to see a picture. So here's the picture that we have. You have an inherent risk and you have a residual risk. And those are both loss exceedance curves, right? But you've also got a risk tolerance. And the idea is that you stochastically dominate your risk tolerance with your residual risk. That means every point on the residual risk curve should be below and to the left of your risk tolerance curve. So this is a simple visual way to say, look, under is good, be under. Over is bad, don't be over, be under. If you breach the risk tolerance curve at any point, you say that that part of the risk is unacceptable. I have to do something to mitigate that risk. So you add mitigations and you reduce the risk. You've got residual risk left over, and you monetize the difference, how far those two curves moved. Okay? So that's one way to express it. It's mathematically unambiguous. It's easy to check. There's a lot of other things you can do. You can make it more elaborate. Sometimes you have risk-return trade-off, and so modern portfolio theory has a risk-return trade-off. You could think of this as a surface where there's a variety of risk tolerances given different possible returns, but you can make it as complicated as you want. Okay?
If I could just add, our thinking is perfectly consistent on this.
Okay.
We both recognize that when you're speaking of risk, you're expressing risk in the form of a curve. The risk tolerance curve needs to lie above your estimated risk curve, and your estimated risk curve includes a before and after component. So
good.
Our thinking is perfectly consistent. We use slightly different terminology,
Sure.
but consistent terminology.
Yes, good. Inherent risk and residual risk is more of an information security terminology. Sometimes people talk about risk post and prior mitigation. It's different in different industries. So the neat thing about that is now we can do the math with it. I can do my risk curves for individual systems, let's say, and roll up my risk curve for a portfolio, maybe a project portfolio or a company portfolio of different systems and events. Maybe each of the divisions or something has their own risk curves, but I have a risk curve for the whole company. So you can do the math, you can add them up. All right? So why don't we do this more often? We've already acknowledged that there's lots of problems of different sorts. We're overconfident, we're inconsistent. We have other kinds of errors we introduce that I'll get into in a little bit. So why don't we use more quantitative methods? We talked about some of these yesterday during the panel. We don't have sufficient data to measure that. Or each situation is too unique and complex to apply scientific analysis or historical data, Has anybody said any of those or heard them? All right. So remember my response yesterday, we don't have sufficient data. That's actually a pre-math judgment that people make. If they did the math, they would usually be surprised by how much uncertainty reduction they get from a given amount of data. But here's another important thing. Science isn't really just about having data. It's about getting data. That's why you do controlled experiments and samples and surveys and go out into the world and make observations. I mean, if we were stumped, think about the early scientific revolution. If they were stumped because they didn't have Oracle databases filled with empirical data already, what would have happened? No, you conduct experiments, you go out into the world and make observations, real measurements. That's where you get the data. We're not saying you already have to have the data, you can get the data. Each situation is so unique and complex that we can't extrapolate from historical data. Remember yesterday my comment in the panel was, remember the implied alternative is that therefore we're better off relying on our experience. In all these cases, when someone makes any of these objections, they're saying, therefore we're better off relying on our experience, or the qualitative method I was using. Okay? Remember, you're never in a case of whether or not to use a method. You're always using a method. The question is, what's the measured performance of the methods? we should choose the method that measurably outperforms the other. And of course, we should see the irony in these two claims, right? I can't extrapolate from historical data, therefore I have to rely on my experience. Ali was mentioning yesterday, that's actually what experience is, of course, but, or I think Jack might have mentioned it, but of course, experience is only historical data, just with selective recall and flawed inferences, all right? And worse yet, you can do worse than that, though. If you use a qualitative method where the components have already been measured and they actually add error, somebody was asking me, what do you say about the garbage in, garbage out response? I say, perfect. Nobody gets away from that, though. Your expert intuition doesn't alleviate the garbage in, garbage out response. The problem is some methods are garbage in, add more garbage, garbage out. That's what you don't want, okay? So we're controlling for some kinds of errors that come up in our decision making just by doing the math right, first off. But also training people for overconfidence and controlling for inconsistencies in their judgment. So I talked about this yesterday. This might be a little boring for the people who sat with me at lunch yesterday, but I've asked groups of biostatisticians this. Here's a large organization. Who's from a really big organization? Tens of thousands of people. How big? 100,000. Here I sample the entire organization. I get 5 samples of people spending X minutes a day on some activity. Maybe it's security-related activity, or maybe you're trying to assess how much time they spent in something that they would be denied if there was an outage, and so you're trying to assess impact or something like this. But you had a lot of uncertainty. You had no idea how much time people spent on this. So you randomly sample 5 people. Now suppose I'm trying to estimate the median of the entire population. Remember the median? That's the point where half the population is below and half is above. So I just sampled 5 out of 100,000 at Verizon. Number one, is this statistically significant? I think we led on yesterday. I see some heads shake. No. Remember, if you say no, it's only because you don't remember what you learned in statistics. This could easily be statistically significant. I haven't told you the hypothesis or computed a p-value or given you a significance level. You need all of that to determine whether or not that's statistically significant. But here's the, actually, and there's a whole different philosophical discussion about statistical significance, that you don't really need it for decision making. It's a completely different arbitrary kind of, it's really only relevant for getting published in peer-reviewed journals. It has nothing to do with your uncertainty about choices you're making, okay? We can get into that. It's a very different kind of an issue. So here's a more relevant thing. How confident should I be that the median of the entire population of 100,000 at Verizon is somewhere between the largest and smallest sample of this, largest and smallest value in this sample of 5? Anybody have an idea? 50%. That's not an uncommon response. The actual answer is 93.75%. If I take a random sample of 5 of any population, regardless of how the population is distributed, it could follow any distribution. This is a non-parametric method. It doesn't care about the distribution. I'm just trying to assess the median of the population. It could be distributed anyway. Random sample of 5, there's a 93.75% chance that the median of the entire population falls between the largest and smallest of a sample of 5. In my first book, I call this the rule of 5. But there's actually a mathless table I give too. If you sample 8, you take the second largest and second smallest. You sample 11, you take the third largest, third smallest. And you can estimate 90% confidence intervals, close up conservative approximations actually, of 90% confidence intervals of the median of a population based on those samples without doing any math. You just look up your sample size in the table. I call it the mathless table. The chief statistician at the EPA, I did a project for him, didn't believe me until I showed him the simple math behind it. He said, there's no way that can possibly be. And I said, no, here's the math behind it. So, and if you don't believe me, we'll set up simulations in an Excel spreadsheet, and we'll bet real money, and I'll play till you run out. Okay? Here's a harder one, though. This is a harder one. This is an interesting example, though, of where our intuition contradicts the math. If your intuition contradicts the math, well, you should check your math, but it's not the math that's wrong. The question is, why is our intuition wrong, right? So here's another one. I've got a warehouse full of urns of marbles. Okay, I call this the urn of mystery in the 3rd edition of the first book. So I added the urn of mystery to it. So each of these urns is filled with 10,000 marbles, let's say. And all the marbles are red or green. And the percentage of green marbles in the population of marbles varies from urn to urn. And it varies all the way from 0 to 100% uniform distribution, right? And there's thousands of urns in this whole place. So I randomly select an urn out of the warehouse. I put it down between us. It's opaque. We can't see into it. And John, I'm going to bet on the majority color here. I'm going to say the majority color is red. What's my chance I'm correct? There you go, 50-50. Now, I'm going to give you a deal. We're going to do this over and over again in the whole warehouse. I'm going to give you 2-to-1 odds, okay? Every time I lose, I pay you $20. Every time I win, you pay me $10. You'd take that bet, right? Yep. Absolutely you would. So I'm going to ask you for one little favor. I'm going to get to randomly sample. I'm going to get to randomly sample a single marble, one marble out of each urn of 10,000 marbles before I make my decision. And based on that single sample of one marble, if it's green, I'm going to say it's majority green. If it's red, I'm going to say it's majority red. Now there's 10,000 marbles in the urns. Now what's my chance of winning, given that I've gotten one sample? Better than 50? Anybody have a guess? I've had a PhD biostatistician say 50.0001%. Actually, the answer is 75% of the time. Now, if you disbelieve me, if you don't believe me, we'll do that little Excel simulation. It's real easy to set up. And again, we'll just play that game until you run out of money. All right? You're right, 75% of the time based on a single sample of one. Okay? And a lot of times people get concerned about how much data they need, or I need really good data. Well, wait a second, have you done the math? Have you figured out how much you can infer from a few data points? Because if you have a lot of uncertainty, a few data points are sufficient to significantly reduce your uncertainty. So here's something that Daniel Kahneman, everybody heard of this guy, right? Won the Nobel Prize in economics in 2002, but he says he never took an econ course in his life, right? But he actually did the work that started behavioral finance and behavioral economics. And here's what he says, and something he published way back in 1971. Even when he was testing people who've been published in peer-reviewed scientific journals, he says people have strong intuitions about random sampling, and these intuitions are often wrong in fundamental respects. So in other words, you know, even if you got a PhD in biostatistics, you should probably do the math before you. So there are some important consequences for this. One researcher, Robin Dillon Merrill, looked at the way that engineers at NASA were interpreting near misses prior to the Challenger and Columbia disasters. So almost every launch, there was a loss of tiles, there was a big chunk of frozen insulation falling off the external tank, or there was at least damage to an O-ring. Okay? Now, 2 of those 3 reasons were reasons for the Challenger and Columbia disasters, right? How were the frequency of near misses being interpreted by the engineers? Here's what they thought. Every time the shuttle comes back without catastrophic loss of crew and vehicle, that's what they call it, loss of crew and vehicle. Every time the shuttle comes back and lands safely, even though there was a lot of near misses, that must be evidence that the system is more robust than we thought. So I actually did the Bayesian analysis on Robin Dillon Merrill's work, and I saw that what I said was, if you saw the near misses every launch, and you have uncertainty about the launch failure rate, and you also have uncertainty about the near miss rate, and you have uncertainty about the conditional failure rate given near misses, but each launch you see some near misses and a lack of a failure, how should you be adjusting the chance of a catastrophic loss of crew and vehicle? Well, the first few missions, you should actually be increasing the probability of catastrophic loss of crew and vehicle. It'll actually take all the way out to 50 safely returned missions before it gets back down to what you thought it was in the first place, about 2% chance. But managers, according to the Feynman study, managers were, executives at NASA were actually thinking there's more like a 1 in 50,000 or 1 in 100,000 chance of loss of crew and vehicle. They're way out of whack with the risk models. So even quantitatively sophisticated people were making inference errors about how to interpret near misses. So there's a way we can deal with this. This is a low resolution Bayesian analysis example. I made a spreadsheet for it. I talk about it in the 3rd edition. And by the way, the spreadsheets that I talk about in the 3rd edition are all downloadable for free off the book's website. I just point you to those and you can download them. So what you can do is if you have some prior opinions and you've been calibrated about the likelihood of different kinds of population distributions, every single observation reduces your uncertainty a little bit. So in this particular case, I'm drawing from 4 possible population distributions. And every sample I pick reduces my uncertainty a little bit about which of the 4 population distributions I'm drawing from. Now, of course, it doesn't have to be just 4 population distributions with 4 clunky bins. It could be thousands, right? We can do all this. So here's just a few things to remember about empirical methods. I talked about this yesterday, but just assume it's been measured before. Assume you have more data than you think. Remember the uniqueness fallacy we talked about yesterday. And given the examples I just talked about, you need less data than you think. These are very productive assumptions. They're almost always right. Just assume them, just use them as a working assumption for a full day before you give up on something about how to measure it, okay? There was, I think it was Gladwell who in Outliers said something like a genius is a person who thinks about something for 20 minutes that other people give up on immediately. Yeah, just maybe 20 minutes even, not even a full day, but for 20 minutes, just make those 3 assumptions. Just work as if they were true and see if you can figure it out, okay? Now, here's another thing we talked about. Often, you might have the impression you have a lot of uncertainty in information security, right? And sometimes people get the impression, we were talking about having a statistically significant sample size yesterday. By the way, that's an incorrect phrase already. There's not a statistically significant sample size. And it's certainly not 30. They're just misremembering statistics whenever they do that, okay? So if you want to trump somebody in a business meeting, that's one way to do it. Wait for them to say that and then ask them, do you remember what that actually means? Just define it for me. So you have a lot of uncertainty. Sometimes there's an impression that if you have a lot of uncertainty, you need a lot of data to reduce uncertainty, right? Do you think that that's an assumption sometimes in information security? I've got a lot of uncertainty, so I'm going to need a lot of data to measure it. Mathematically speaking, just the opposite is true. The more uncertainty you have, the bigger uncertainty reduction you get from the first few observations. In fact, if you know almost nothing, almost anything will tell you something. That's what the math says, okay? So if you chart it out, you can chart out, we actually do these calculations for a bunch of different problems, but you can work out the expected value of perfect information. These are classic decision theory, game theory kinds of calculations, okay? You start making measurements and you go from a state of low certainty to higher certainty until, let's say, theoretically, you could get out to perfect information, just for the sake of argument. You've got this EVI curve, the expected value of information curve. It's going to rise quickly at first, but it has to level off because it can't exceed EVPI, right? You can't do better than perfect, so it's going to level off. ECI, the expected cost of information, actually starts out slow and then skyrockets because that getting rid of those last little bits of uncertainty cost ever more in terms of data gathering. If you've got a lot of uncertainty, the first few samples can significantly reduce uncertainty. If your current range of the percentage of people following some procedure correctly in cybersecurity is 0 to 100%, how many people do you have to sample to reduce that range by half? It's about 9. 9's enough to reduce that range by half. If your uncertainty really is 0 to 100%, you can. But what if your uncertainty right now is 60 to 65%? How many would you need to sample to reduce that range by half? Well, it's many hundreds, thousands actually, okay? There's a huge increase in the cost of additional data for an additional incremental uncertainty reduction. So what this tells us, when you look at these curves, and they're almost always shaped this way. One curve's this way, the other, one's convex and the other's concave, right? This tells us that the optimum value of measurements is much earlier than we think. We get the biggest bang for the buck fairly early, and then we reach the point of diminishing returns fairly quickly. And so we constantly overestimate how much data we need. Now, at Kaiser Permanente, I won't go into this, but we actually built these models based on lens model regressions of expert opinions. We're generating loss exceedance curves, and we delivered our tool as a spreadsheet. Kaiser Permanente then took our spreadsheet as really sort of software specs and used Archer and .NET to turn it into an enterprise platform. So they're actually computing, and one of our other clients is doing this now too. They're actually computing the return on controls by estimating the risk of individual systems, estimating how much risk mitigation they get from particular controls, estimating the cost of those controls, et cetera. And so that's what's giving them a way of estimating how much of a return on mitigation, that's what they called it, return on mitigation. They still went back to using color circles. I always tell them I don't need that, but they thought they needed that to communicate with management. Personally, I find a lot of instances where somebody speaks on behalf of someone else's ability to comprehend math or statistics. They'll say, Doug, you and I get all this stuff. We get it. Those other guys, though, they won't understand any of this stuff. And then I talk to the other guys, and they might say the same thing about him, okay? So everyone speaks on behalf of someone else's limitations, it seems. But, you know, I find that those limitations aren't as bad as a lot of people think. But they did think they needed to have colors on things. That's fine. Doesn't make it, once you do the math right, go ahead and add colors. That's okay. Don't make your decisions on colors. Make the decisions on the math, but if it helps you visualize things. So in my second book, I actually also looked at problems with quantitative analysis methods, because remember, it's not a bad idea to be a skeptic. You should be a skeptic about all modeling methods. And even the quantitative methods we're currently using, we should constantly analyze. We should update them and check them. So I actually interviewed 35 Monte Carlo building experts, and I asked them each for 1 to 3 of their most recent models, and we audited each of their models. So we had to do NDAs and all that kind of stuff. So we actually looked at 72 individual models. And these were people from entertainment industry, engineering, construction, financial portfolio management, commodities, sports, some of them were, et cetera. And they built all these different models in different industries. And we find that while most use a significant number of subjective inputs, none of them had actually heard of calibration. So nobody was calibrating anything. So if you're populating a Monte Carlo simulation with mostly subject matter experts' subjective opinions, and they're overconfident, which is a given if they haven't been calibrated, what does that mean for our calculation of risk? If all of our estimates are overconfident, what does that mean for our loss exceedance curve? We're underestimating it systematically, every model we build, okay? Just because we're relying a lot on expert judgment, we know they're overconfident. None actually tracked the original forecasts of models against actual outcomes. None of the 35. At least none for the 72 models they provided that we looked at. We also calculated information values. I talked about calculating information values for that one, the expected value of information for uncertain variables. We find that when we calculate information values, there's almost always a reason to measure something empirically before you make a decision. That's what that means. In fact, computing the value of information on every uncertain variable in a model is the reason we call the method applied information economics. So there's a lot of interesting findings when you start computing information values on everything. We find out, for example, that people have been measuring all the wrong stuff all along. So how do you figure out what to measure, by the way? Of all the things you could be measuring to inform decisions where you're making big uncertain bets, which things did you figure out to measure? How did you determine that those were the things you needed to measure? Within software development, what do you think they spend more time measuring, costs or benefits? What's more uncertain, costs or benefits? Right, that's a measurement inversion, okay? Within cost, you can break it down further. You don't have to leave it that lumpy, all right? You can break it down further. Within cost, what do they spend more time measuring? Initial software development costs or long-term maintenance and training? Which one's more uncertain? Which one's bigger? So even in benefits and costs, and if you take any pairwise comparison of 2 possible measurements, you tend to find, there are some exceptions to this, but you tend to find that the one with the higher information value is actually given less historical attention in measurements. We call this the measurement inversion. It appears in every industry, every profession we ever analyzed. I don't know how it doesn't affect the GDP. Okay? Also, and Ali knows this, in some industries, significant well-known model errors persist, you know, choosing the wrong distribution for market volatility, et cetera. And also, even, for example, my oil and gas clients, they're pretty sophisticated in building Monte Carlo models for oil reservoirs. So oil fields, they try to estimate the barrels and they try to estimate the rate of extraction based on different systems. They've got uncertainties about rock porosity, water content, temperature, pressure, different depths, and what kind of rock strata they'd have to get through and how much they'd have to spend drilling before they start extracting, and fracture systems in rocks. I'm learning all this stuff in the last couple of years, by the way. Fracture systems in rocks limit how quickly you can get oil out of something. Or whether or not you've got to pump a pressurized fluid down into it to extract more oil, et cetera. They do all this great analysis for how much oil is in an oil field, and then when they try to work out the estimated revenue or profit from a drilling rig, they use an exact number for the price of oil. Now, there is uncertainty about the price of oil. And you know what reason they give? This is actually the reason they give. Well, we don't have any way of knowing that, so we put an exact number on it. Wait a second. You just put uncertainties on all the other stuff you didn't know. You have no way of knowing what rock strata you drill through. But the thing is, these are all geologists and petroleum engineers and reservoir engineers. I found out that reservoir engineers, if you want to get into that field, the reservoir engineer is the one you want to be. They're the really elite. I didn't know this, but that's where the money is reservoir engineers. But when they get outside of their comfort zone, all of a sudden they start making the same errors again, okay? So here's what I mean when I talk about measuring the performance of a model. This is one of our clients. I can mention their name because we got permission to write about them explicitly in the book. This is Life Technologies in Carlsbad, California. They're a laboratory equipment manufacturer, and they make everything from mundane laboratory supplies all the way up to big gene sequencing machines, okay? Things that can do thousands of experiments in parallel and things like this. A bunch of little vials with a robotic arm that's moving around. It's a fascinating area. So they have all this different equipment that they do R&D on to develop new products. And one of the things they have to do to evaluate which R&D projects they should fund is try to estimate the first and second year revenue. So we looked at their performance actually this was the client's own analysis because they wanted to do their own independent analysis. They're scientists, they're molecular biologists, they know how to do this stuff, okay? They know how to test hypotheses, right? So they looked at the correlation between first and second year estimates of revenue and actual outcomes. And then they did that for human forecast, they did it for historical models. Now, human forecast didn't just have a low correlation, they had a systemic error because they were all just overestimating things, right? Historical models at least didn't have systemic error, and the correlation was a little bit better, but the AIE model, which was a combination of these things, actually did measurably better. And this is their own data. This is their own analysis. I didn't do this. So that's how they decided that they should do more analysis like this, okay? So just as a summary, every component of the methods I'm talking about are components that have been individually tested in independent clinical trials run by academics. Because I didn't invent any of the components. I simply selected components that other people had measured the performance of already. And then we added a few things to it to make it a practical procedure that people can implement. If you can explicitly calculate the value of information, you start measuring completely different things. And that by itself is a huge impact on your decision making. We actually, as we should be, as we all should be, we should be quantifying uncertainty explicitly. And we can do it in a mathematically sound way so we can do the math with our portfolio risk, our system risk, et cetera, okay? And I'm actually working, the Kabuchi Desert Project for the UN is actually the 86th risk return analysis for major decisions I've done. And I'm not including in that the cybersecurity risk return models because it's over 100 when I put in other kinds of consulting projects. But 85 are just risk return analysis, building big Monte Carlo simulations, computing information values, conducting empirical measurements, reducing uncertainty, and making the best portfolio bet. So, what's your most important decision? It's how you make decisions. That's your most important decision. You got to pick the best way to make decisions first. What's your biggest risk? A flawed risk assessment. You don't even know it's flawed. Your most important performance metric? How about measuring those things? Or even measuring the return on performance metrics. How about that? And how did you even figure out that those are the performance metrics you should be using? Who uses dashboards in their company, by the way? All right? Great idea, right? How many items are on a dashboard? A dozen, couple dozen, a lot of data there. How did they figure out that those were the things they needed to see to inform their decisions? I bet they didn't compute information values and use that to figure out which dials and charts ought to be on their dashboard, right? They probably didn't do that. So what's the whole strategy with the dashboard? Here's the strategy with the dashboard. I wrote about this in the first book, so this is a new thing for me. I'm criticizing dashboards a little bit. I think it's a great idea. I think they're poorly executed. Even if they look nice, here's what's wrong with dashboards. The strategy is, if I just saw these 20 things, I hope I will know what to do when the right conditions arise. I hope I'll be able to identify those conditions when they arise. They haven't figured out in advance any trigger conditions for things, right? They're just saying, you know, if I knew these 20 things, I think I would just have better decisions. That's not a way to pick things on a dashboard. You have to model decisions that information is going to inform, reduce your uncertainty about, and then you have trigger points identified. When those conditions arise, those conditions can be very subtle combinations of several of those variables. So it's not going to be obvious to you right away. So you have to compute those trigger conditions in advance and know what the optimal solution is in advance. All right? Otherwise, you've just got big data feeding a dashboard, feeding what's the weak link in this whole process. It just goes into my head. That's the weak link. I'm measuring with a micrometer and cutting with an axe, right? I'm adding all this additional error at the end. The big data is not doing me any good if I leave that weak link in. So we have to have big decision support to complement the big data. Big data is a great idea. We should use the data we've got. But it needs to go into decision models in order to make the most use of it. All right. Any other questions? I don't know how much time I have left. Oh, okay. All righty, good. Are there any?
Time. Anybody have any questions? All right.
Doug, thanks. Always entertaining and informative. Question for you. So in your experience, how much uncertainty should you try to reduce? And did you feel kind of good enough? You know, Ali was talking about accuracy versus precision yesterday. Do you feel you're directionally accurate enough that you can actually make decisions without having to be precise, right?
Yeah. Well, the good news is there's math for that. We don't have to guess. The math tends to tell us that the optimal amount of uncertainty reduction is a lot earlier than we tend to think. I did a study for the Australian Customs Department, so they're customs in Australia. And they were doing this annual study of travelers to get all sorts of satisfaction readings and how long travelers took to go through security and what percentage of them had these problems. They had 9,000 samples in their survey. Does anybody work in a firm where you hire a big survey company to do big surveys? Anybody do that? Anybody work in that kind of an area? Survey companies never want to sell you a small survey. What's the point of that, right? 9,000. Given the decisions that they were actually trying to support, they were better off with about 100. I mean, even 100 could be a massive overkill in some other areas. In some areas, 15 or 20 is an uncertainty reduction that gets you to the peak, the optimal uncertainty reduction. Obviously, you can visualize here, if I subtracted the ECI function from the EVI function, and I have a net benefit of information function, I'd have something that's got a peak here. I solve for that point, the optimal point. But actually, I don't even really have to usually do that in advance because I don't have to commit to sample sizes in advance usually. I can do one sample at a time, and we've done this many times. I can do one sample at a time and compute the value of one more sample. And then keep sampling until the value of the next sample is less than the cost of the next sample. It's just that algorithm terminates measuring much earlier than we usually think. So yes, there's an answer to that. Computing the economic value of information is a way to do it. The formula is big and long looking sometimes. I have the discrete general form of the formula here on a slide somewhere. But the concept is very simple. There's a chance of being wrong and there's a cost of being wrong. It's really kind of a decision risk think of decisions having a loss exceedance curve by themselves, okay? I can be wrong by a little bit or I can be wrong by a lot. And when I have a big cost of being wrong and a big chance of being wrong, the value of information tends to be higher. That makes perfect sense, right? So all of the, they call that the expected opportunity loss when they compute, this is all decision theory stuff, when they compute the expected value of information or expected value of perfect information. So that's how they figure out what they need to measure and how much to measure. Because the first question is that even the right thing to measure? Because chances are, given all the other observations we've made to date, that they may be measuring the wrong things already. So forget about how many samples you need. Those aren't any of the things you need. First, you select the right things to measure, and then you can optimize your sample size. Okay? Any other questions? Pat.
I'd like to ask you about the NASA example. I
Oh, sure.
remember the famous story of Richard Feynman with the glass of ice water and the rubber band about the O-rings. Now, did Feynman get it wrong about the probability of accident, or was he even involved with that?
Well, he's actually the guy that wrote the report where he was interviewing NASA upper management, and they were telling him, we thought the chance of a catastrophic failure was like a 1 in 100,000. So he actually wrote that in the report. He got that from direct interviews with people. Let me go back to that. Here we go. So let me explain a little bit about that NASA example. Well, this is a different example because this is not the shuttle. In that particular example, I like that example because Feynman did a controlled experiment live on TV. By the way, if you start thinking that well, we can't do a controlled experiment, that's too much work to do. We've done a controlled experiment in the morning. We do it before lunch, okay? Feynman did it live on TV with 2 C-clamps. And each C-clamp had a sample of O-ring material, and he had them compressed. But one C-clamp was dipped in a beaker full of ice water. He said, live on camera there, he said, I put these O-ring samples in C-clamps earlier this morning, and I put one of them in ice water. And he pulled them out right there live. He didn't know what he was going to see. And he undoes the one that wasn't in ice water, and it springs right back. So it springs back to its original shape. He took the one that was in the ice water, unscrewed the C-clamp, and it was still compressed. It wasn't springing back right away. Now, what was his sample size there? 1 in the control group, 1 in the test group. Okay? Now, you can argue if you want with a guy like Richard Feynman about whether or not he had statistically significant samples. Good luck. Okay? I think he knew what he was doing. All right? He has 1 more Nobel Prize than the rest of us, I think, combined. Okay. Unless there's somebody here I don't know about. But yeah, that's a very simple controlled experiment. He reduced uncertainty. He was just testing a hypothesis. He just thought it was interesting. He wasn't drawing any conclusions yet. He just thought it was really interesting. He says, I wonder what this means. Well, of course, it ended up that was the issue, right? So, later on, you see guys like Feynman, and then also you see some data people like Tufte, right? Who are showing that when you included the cold days and the hot days and the times the O-rings were damaged and the times they weren't damaged, you do this logistic regression, and you find out you probably should have launched that. You probably should not have launched that day. Any other questions? That's a matter of doing the math right, right? I mean, they're NASA engineers. They're smart guys. It's just a matter of doing the math right with simple statistics. This isn't even second semester statistics. That's first semester, okay? Question?
So I think one of the challenges that I've seen in the information security area is even once you figure out how to measure individual risks and start getting that method down, you have a very large set of risks that apply to any given company or enterprise. Is there any additional methodology, tips or tricks that apply to when you start rolling those up into a portfolio and how to manage that that's different than just looking at each independent risk by themselves?
Well, first off, some is better than none, right? You don't have to boil the ocean. I mean, each month or quarter or year, you can add more risk. That's the best thing about it. It's hard to do that in your head, by the way. So remember, we're always comparing it to the alternative. How are you doing that in your head? How are you doing that with a qualitative method where you're not even doing explicit math on these risks? You're definitely getting it wrong. So at least let's start getting it right. You can roll it out. What we tend to do is we tend to focus on high return areas, particularly risky areas. We solve that first, right? And then we keep doing things. We have a rollout plan. With our biggest clients, our Fortune 10 clients or so, our biggest clients, we don't turn on a switch and everyone's using it. We have a rollout plan. We have a whole method even for identifying and adding new risk and continually updating the model. And every time they have an observation about a breach or an impact of some kind, that updates the model, all right? So you're not done when you start doing this. You're implementing a process, okay? 10 years from now, you'll be identifying risk. That's fine. You're not done with it. The process is what's important. Eisenhower said something like, the plan is disposable, planning is indispensable. Something like that. But I almost feel a little bit like that with models. So your model is just an immediate improvement on what you're currently doing. But you keep modeling. The model's never done. The point is doing the modeling, okay? Any more questions?
We have time for one more if anyone has one more they want to
question.
sneak in. All right.
Let's do a real hard one.
Yeah, I don't know.
Yeah, really.
Well, we have about 8 minutes before our next presentation, so I think we should give you a huge round of applause. That was outstanding.
All right,
Thank
thanks.
you.